So getting to that is maybe not that hard. I mean, then you have to actually do the actual work, but I want to do still show you how you get there. So also you can for yourself with other things. Let's say X is a Toric variety. So I mean an equivariant compactification of the algebraic torus so this means my toric variety and my torus acts on the toric variety, and the torus is contained in there as an open dense subset, and the way the torus acts on here extends the action of T on itself. And we let M from T to T be the character lattice. So then one nice thing is that ample line bundle corresponds to lattice polytopes in this lattice over there. So A is an ample line bundle from X. Then in the toric case, this implies A is fully generated. So this is very special for the toric case. And there exists a lattice polytope. A. The A lives in the M tensor vector space, which has the lattice M. And the nice thing is that the global sections of our line bundle are given correspond to the lattice points in my lattice point. So this is a character corresponding to U. Here, and that corresponds to a character. Okay. So it's a fact that a toric variety has finitely many torus invariant prime divisors. Torus invariant. Oh, I forgot to tell you, it was 74. 74.
Right.
You get all by me, Anyway, so X is finally the torus invariant divisors. Torus invariant prime divisors. So I tend to forget to say the prime. I always mean it. No, that's not true. D1 up to Dn. And for each of these divisors, we can associate a facet of our lattice polytope. And the facet, so if you know toric geometry, then you sort of know what the facet is. If you don't know, then you can describe it as follows. So P rho is equal to pi to the U in the global sections such that the order of along D rho of chi to the U is minimal. We call this D rho. facet. Okay, and so if we take n and Z is the dual lattice, and we roll in NR is defined as well. So let the vector orthogonal a row facing into the table. So if my polytope looks like this, right? So this is my PA row 1, and this is V row 1. Then we have the following criteria for stability. So the proposition is Tx is semi-stable with respect to A if and only if for all subspaces F of NR generated by subsets of the V rows we have the following inequalities, that the sum over all the V rows in F, the volume of P row divided by the dimension of F is less than or equal to the no, equal to 1 to n of all the facets. So we can take the volume of all the facets. So A is fixed. So this is always with respect to the polytope over dimensions. So this is how you can sort of reduce checking stability of tangent bundles. We have our A, right, and the information of the tangent bundle is sort of hidden into these V rows. I will hope I can get to explaining this later on. This is the check you have to do. Diane said, there's this nice combinatorial condition for K stability. So K is a toric funnel, and this is K stable in if and only if, so this is P M1 and 2 P as barycenter in the origin, and then we saw, nice. So Donaldson's theorems is Donaldson Chen-Sun now gives us that if corollary P minus Kx as barycenter in origin, then this implies that this condition is satisfied. I mean, this wasn't easy to prove. And then it turned out that Benjamin had a colleague, and he had written a paper about this before. This was Hank and Lincoln, and the combinatorials had studied this before. And this is these kind of conditions are called subspace concentration conditions, and they come up elsewhere. And yeah, I don't know. That's pretty fun. So you can do it, but it's hard work, you know. It's not like an easy combinatorial proof. Okay, so I want to show you now where this where we get such a formula from. Okay, so toric vector bundle. So here toric vector bundle. Okay, so this is E on X. And we want that the torus, right? The torus acts on here. So we want that the torus also acts on E. And it acts compatible with the action on X and linearly on fibers. So. And then Piatko found that there is an equivalence of categories. So on the one side, we have E, the toric vector bundles. On the other side, we have E and a vector space, sorry. And for each torus invariant prime, you guys only get a decreasing filtration. Some people also do decreasing filtration, but I usually do decreasing filtration. For every torus invariant prime. And then we also want a compatibility condition. Okay, so
what are the morphisms?
Morphisms?
Yeah, on each side.
Here, these are morphisms E to F that respect the torus action. Here, the morphisms are morphisms of vector spaces such that the filtration of here gets mapped into the filtration of the other one. So I will show you now how out of the toric vector bundle you can get at least part of this data. So it's not coming from nowhere. So the compatibility condition, I wanted to write down, but I'm a little bit pressed for time, I think. So it's basically what you want is for every maximal torus invariant affine subset, you want to have a decomposition of E into a direct sum of subspaces. One-dimensional if you want, you can make them one-dimensional, such that for each divisor that meets this torus invariant subset, the filtrations are direct sum of your splitting of E that you have found for this. So so you can write E as a direct sum P1 plus PR locally, and every vector space in the filtration is going to be a direct sum of some of your bundles here, but only for on your open subset, and only for the divisors on your that contain your open subset. If you go to another maximal open subset, you have to take a different splitting. But we won't use this so much, so this is why I'm not saying all of this. We won't use it at all, actually. So, okay, if E is a toric vector bundle, how do we get this data? So, what is our E? This vector space E is the fiber over the identity. So you have the toric variety X and X, right? And then you have here the torus, and then you have the boundary divisors. And in the torus, you have the identity, and you can take the fiber over the identity. And you can also take E restricted to T, the global sections of this. And this has a natural T action, and you can take the torus invariant part of this. Which you will prefer. So this is just the okay. And what is the filtration? So now for torus invariant prime divisor, I have to tell you what does this filtration look like. So which of these the elements in here in the fiber over the identity are in the ith part of the filtration corresponding to this divisor? Well, so I take my E, so I have, say, an E here, and I can spread it around the torus. So I can spread it around the torus to make a section SE, and then this has a unique way to extend to the right. So SE T extends section. Yes. And so this is equal to those E, such as the order along D of SE greater than how you get the filtration. Okay, and Herling actually said, so if you look just at reflective sheaves, so reflexive sheaves, they just correspond to E, ED of E filtration, decreasing filtration. So there those, they don't need to satisfy this compatibility conditions. Okay. So, stability of toric vector bundles. First, are there any questions about this? You can take it as a black box. So now you can express a lot of things about toric vector bundles in terms of this data of these rotations. So this is what we're going to do. So stability of toric vector bundles. Toric vector bundles. That it has been studied already early on, but somehow it stopped. So it's theatrical in 98. So on P2, and he uses to study Horn's theorem, so the Horn problem, and yeah, in the end there was a different proof of this due to Knudsen and tau. But at least this, and then Knudsen and Sharp. Also in 98, and also whole study more physical stability. And so what they all did is they compute the term class. Let's follow. So, and then you can get the following formula for this slope. So X is smooth toric variety. And A ample on X. B toric vector bundle, you know, with the corresponding filtrations. Oh, I can hear this. Let's see. Yeah, we need for those. And P is polytope associated to A. Then we get the turn class as follows. So we get mu of E, sorry, the slope. I will stop that. Maybe let me remind you what this was. So C1 of E times So there's one over the dimension of E. Then you take the sum over all divisor. Then you take the sum over all I and Z. And then you take the I of the dimension of ED of I minus the dimension of ED of I plus 1. And times the volume of P Do I call it PD or P row?
Zero.
Row.
Yeah.
Okay. And these are all rows. So the rows correspond to the okay. Good. And so this is a finite sum because, of course, E is a finite dimensional vector space. So this can only jump down finitely many times. And so this is a nice finite sum. And so why is this? So what goes in here is that the first term class of E has this formula. It's the sum over all rho, sum over all I dimension of rho of I. One. Rho, and then it's a well-known fact in intersection theory that D rho times A D rho plus D rho dot A to the dimension X minus 1. So this is given by the volume. So this is with this. This actually needs some calculation, so this is not like sort of immediate calculation. But yeah, so we can get this. Okay, so we have the slope. So in order to check whether something is stable, we have to compare the slopes of subbundles, right? And here we are in good shape because it turns out that we can take, as we don't have to take any subshapes, we can just take equivariant subshapes. And amongst those, we can also take very simple ones. So then E is a toric vector bundle. Actually, yeah, this should also work for a vector sheet, which is, I don't know, I've never used it for this. Is semi-stable, stable, even only if for every linear subspace S and E and F rho of I equal to E rho of I intersect F. So you get the filtrations just by intersecting F with these filtrations for E. We have that 1 over the dimension of F, again, of this horrible sum here. I dimension F rho of I plus 1. I volume 0. It's less than equal to 1 over dimension. Okay, so the point here is first of all, is that we just have to check these particular subspaces. So they just claim this, but actually you have to prove a little bit something here, because like every, you also have to, so first of all you have to check that it works for that it's enough to just check so enough to check torus equivariant subsheaves. And this is because the subsheaf, so there exists a maximal destabilizing subsheaf, so that satisfies that for let's call this F, that for every G, so E is the coherent shape here. So for every G, the slope of G is greater than or less than or equal to the slope of F, and if the slope of G is equal to F, the slope of F, then G has to be equal to F. And the fact is, this exists and it's unique. And now you can argue, well, I take my maximal destabilizing subsheaf, I act with my torus on it, and if I act with the torus on a toric sheaf, I get the same Chern class, I get the same rank, so it has the same slope. It has the same slope, and so and so you can argue that since this subsheaf has to be unique, they have to be the same. So this has to be torus invariant. This subsheaf.
I think I missed the sentence. Why does it? Is there a reason, or is it just something you have to show? So this I feel like I missed one sentence. Sorry.
You have to show a little bit more, right? So you show that it has the same slope.
Okay.
And
isn't that for every G?
Oh, but it's also reflexive. So this sheaf, okay. So this sheaf is going to be sorry, not reflection, saturated.
Okay.
Yeah. So the maximal destabilizing subsheaf is going to be saturated, and that is unique.
Okay.
You act with the torus on it, you get something of the same slope, and it's also saturated. And so since it's unique,
okay.
it has to be the same.
Yes.
Of
Thank
course,
you.
this is a fact. You know, there you have to show something.
Yeah. Thanks.
Yeah.
Yeah.
Okay.
Yeah. Is there a reason why you put the I and I plus 1 from the other board to this board?
Oh no, this would be an I now. Yeah.
Oh, okay, good.
Yeah. I plus 1.
Okay.
Thank you. You're welcome. Did I do it again? No, no. Okay. Okay. Good. So, yes. Okay. And now the next thing we claim, well, it actually suffices to check just these subspaces. And to check just these subspaces. Suffices to check subspaces of the form subsheaves with filtration are of the form F intersect E rho of I. And I don't know, previous sources just said this, but it's not obvious. So I mean, so you can do a combinatorial argument, so there's one way around this to show that this has to be true. This is what you do in, or you show that that's what we do actually as well, is that these exactly correspond to saturated subsheaves, and then there is a well-known fact that it's sufficient to check saturated. Fact, another fact. Okay. But these are still infinitely many, right? So we still have all of these spaces. So this is not great. And then there's a theorem. I don't know. Today and I don't know. Also Diane had some. Yeah. So for every E, there exists a finite set of subspaces F1 Fs in E such that E is semi-stable. This is only if so okay, so let's say Fi is the sheaf corresponding, the reflexive sheaf corresponding to the sheaf. So there's a reflexive sheaf in the correspondence, so I get some filtrations here, and then I have this equivalence of categories, I get a sheaf out of it. And there exists an algorithm producing these subspaces. It needs Grubner basis though, right? You think like this is a nice combinatorial thing, but this needs Grubner basis. So this is not an easy thing. Oh wait. Okay, so back to the tangent bundle. Yeah, so that's also a question, is to find sort of some inherent set of subspaces that work here. That would be nice. But like for the tangent bundle and also for the syzygy bundles, we have found them. So they're, nice subsets that we have to check, and they're nice parameters. But of course, we need to have it in general. Okay, so in the tangent bundle case, so what does the tangent bundle correspond to? In the correspondence, so the finder of the tangent bundle over the identity, you can think of as NC. So N, right? So this was N was C. So these are the one parameter subgroups of the torus. And then for one parameter subgroups, you can take the tangent vector as the identity. So that is the identification here. The tangent bundle corresponds to NC. And then you can check that the filtrations are using Euler's sequence. That Tx of rho of I. So again, Rosen divisor is equal to NC if I is less than 0, if 0, J is equal to 1 and 0, J to 2, and I J. And so now we can compute these differences of dimension Tx of rho of J, dimension Tx of rho of J plus 1. So this is equal to the dimension of x minus 1, if J is equal to 0, and it's equal to 1, if J is equal to 1 and 0 else. And if F is a F is a proper subspace. Then F rho of J is equal to F if J is less than 1. Let's span the rho. So this is if the rho is an F. If J is equal to 1 and 0, if J is greater than 1, and if the rho is not an F, then you get that this is equal to F if j is less than 1 and 0 if j is greater than or equal to 1. And so these the differences of the dimensions, well, I think you can see it sort of from here. So the differences of the dimensions really only depends on whether the row is an F or not. So this is why it's enough to check stability for tangent bundles in terms of vector spaces that are spans of these zeros. Okay, that's all I wanted to say.